Now, although there are three lone pairs of electrons on the fluorine atom in a HF, but there is only one hydrogen atom attached with the fluorine atoms. As a result, we say that on average, each HF molecules can form one hydrogen bond. It can only form one hydrogen bond. While for H2O cases. The H2O case, there are two lone pairs of electrons on the oxygen atom in a H2O molecule. Two hydrogen atoms attached to oxygen atoms. So there are two hydrogen bonds on average. So two hydrogen bonds on average. While for ammonia, going back to ammonia, although it has three hydrogen atoms attached to the nitrogen atom, so there are only one lone pair of electrons. So it can form one hydrogen bond on average for each NH3 molecule. Now, that is HF, it can form one hydrogen bond, and NH3, it can form one hydrogen bond per molecule. Because this one is just got one hydrogen atom on HF molecule, while nitrogen is got one lone pair. However, for H2O cases, the H2O cases, it can form two hydrogen bonds per molecule because it's got two hydrogen atoms and two lone pairs. As a result, it can form two hydrogen bonds on average per H2O molecule. Now, this will affect their boiling points as well. The hydrogen bond strength, we can compare like that way. Arrange the following order of increasing hydrogen bond strength. Now, the hydrogen bond strength HF is greater than H2O, and then H2O is greater than NH3 because of the electronegativity difference. F has a higher electronegativity than O. O has a higher electronegativity than N. As a result, HF has a higher hydrogen bond strength. But don't forget, H2S actually has no hydrogen bond. So we cannot say, it's arranged H2S in the hydrogen bond strength. So the hydrogen bond strength depends on the electronegativity difference. However, for the boiling point, we found that H2O is greater than HF, while HF is greater than NH3. Why is it so? The boiling point is not the sequence of HF. The HF and H2O are different, are just reversed. So the order, it is because HF can form one hydrogen bond per molecule. NH3 can form one hydrogen bond per molecule. However, H2O can form two hydrogen bonds per molecule. As a result, H2O has more hydrogen bonds per molecule. Hence, remember two essential requirements for the formation of hydrogen bond. One is the hydrogen atom. The first one is must contain hydrogen atom, and that atom, hydrogen atom, should be attaching with the high electronegativity atom, for example, NOF. And then the next one, the hydrogen bonds is bonding to the lone pair of electron on NOF. So the hydrogen bond actually, it has two criteria. These two criteria must be present. One is hydrogen atom attaching to a highly electronegativity atom. And two, an NOF, which has the lone pair electrons on it. The hydrogen bonding in water. In water, the molecules are constantly in constant motion. The hydrogen bonds are formed and broken continually. The arrangement are random. So, as the hydrogen bond presence in water, so H2O has a higher boiling point than expected, and then it has extensive hydrogen bonding on water between the water molecules. A larger energy is required to overcome the hydrogen bonds. As a result of that, we will find that it has a higher surface tension, and then this high surface tension, that is because they have great intermolecular force with each other, and then they are difficult to separate. So when you press on it, it's just like the surface tension there, and then it will hold each other firmly. This causes why some of the time you can put the paper clips on the water surface, although it is made up with iron, because or a needle, because the surface tension hold the stuff. While the liquid composed of molecules with strong intermolecular forces have high surface tension, they have extensive hydrogen bonding between water molecules. So it has high surface tension. So that's why the droplets, the water appears like droplets as well. While some of the time you can see the insect can walk on the water surface. The water molecules are held strongly by the hydrogen bonding. That's why there are a lot of hydrogen bondings there. The leg of the insect can still on the water surface. So here we can see Bacillus. So it can walk on water. Let's take a look. If you have heard that, the basilisk lysis, sometimes it's called Jesus Christ lysis, because Jesus Christ has demonstrated he can walk on the water, but the basilisk lizard also can walk on water because of the water surface tension. And for the water droplets, because the surface tension holds the water molecules with each other, as a result, it has a droplet form instead of dispersed on the surface. Also, it affects the viscosity of the water. The viscosity is the resistance of a liquid to flow. And then the higher the viscosity of a liquid, the more slowly the liquid flows. As a result of that, how can we measure about that? We can put a ball, some metal ball, steel ball, and then from the burette and see how long it go to the bottom and or in the measuring cylinder. So it can see what is the viscosity of the water and compare with hexane. It is due to the hydrogen bonding and the van der Waals force. Water is more viscous than the hexane.